Section 11.5, Vapor Pressure. Molecules can escape from the surface of a liquid into a gas by evaporation. Suppose we conduct an experiment in which we place a quantity of ethanol in an evacuated, closed container such as that in Figure 11.22. The ethanol will quickly begin to evaporate. As a result, the pressure exerted by the vapor in the space above the liquid will begin to increase. After a short time, the pressure of the vapor will attain a constant value, which we call the vapor pressure of the substance. Figure 11.22, illustration of the equilibrium vapor pressure over a liquid. In A, we imagine that no molecules of the liquid are in the gas phase initially. There is zero vapor pressure in the vessel. In B, after equilibrium is reached, the rate at which the molecules leave the surface equals the rate at which the gas molecules return to the liquid phase. These equal rates produce a stable vapor pressure that does not change as long as the temperature remains constant. Explaining vapor pressure on the molecular level. The molecules of a liquid move at various speeds. Figure 11.23 shows the distribution of the kinetic energies of the particles at the surface of a liquid of two temperatures. The distribution curves are those shown earlier for gases. At any instant, some of the molecules on the surface of the liquid possess sufficient kinetic energy to overcome the attractive forces of their neighbors and escape into the gas phase. The weaker the attractive forces, the larger the number of molecules that are able to escape, and therefore the higher the vapor pressure. At any particular temperature, the movement of molecules from the liquid to the gas phase goes on continuously. As the number of gas phase molecules increases, however, the probability increases that a molecule in the gas phase will strike the liquid surface and be recaptured by the liquid, as shown in Figure 11.22b. Eventually, the rate at which the molecules return to the liquid exactly equals the rate at which they escape. The number of molecules in the gas phase then reaches a steady value. The pressure of the vapor at this stage becomes constant. The condition at which two opposing processes are occurring simultaneously at equal rates are called dynamic equilibrium, but is usually referred to merely as equilibrium. A liquid and its vapor are in dynamic equilibrium when evaporation and condensation occur at equal rates. It may appear that nothing is occurring at equilibrium because there's no net change in the system. In fact, a great deal is happening. Molecules continuously pass from the liquid state into the gas stage and from the gas state into the liquid state. All equilibria between different states of matter possess this dynamic character. The vapor pressure of a liquid is the pressure exerted by the vapor when a liquid and a vapor are in dynamic equilibrium. Volatility, vapor pressure, and temperature. When vaporization occurs in an open container, as when water evaporates from a bowl, the vapor spreads away from the liquid. Little, if any, is recaptured by the surface of the liquid. Equilibrium never occurs, and the vapor continues to form until the liquid evaporates to dryness. Substances that with high vapor pressure, such as gasoline, evaporate more quickly than substances with low vapor pressure. Liquids that evaporate readily are said to be volatile. Vapor pressure and boiling point. A liquid boils when its vapor pressure equals the external pressure acting on the surface of the liquid. At this point, bubbles of vapor begin to form within the liquid. The temperature at which the given liquid boils increases with increasing external pressure. The boiling point of a liquid at 1 atmosphere of pressure is called a normal boiling point. From Figure 11.24, we see that the normal boiling point of water is 100 degrees Celsius. The boiling point is important to many processes that involve heating liquids, including cooking. The time required to cook food depends on the temperature. As long as water is present, the maximum temperature of the food being cooked is the boiling point of water. Pressure cookers work by allowing steam to escape only when it exceeds a predetermined pressure. The pressure above the water therefore can increase above the atmospheric pressure. The higher pressures cause the water to boil at higher temperature, thereby allowing the food to get hotter and cook more rapidly. The effective pressure on boiling point also explains why it takes longer to cook food at higher elevations than at sea level. The atmospheric pressure is lower at higher altitudes, so water boils at a lower temperature and foods generally take longer to cook.